All right, so I want to just do one problem with you today, and the topic is volumes with cross sections. So we've now done volume in a couple different types of ways, but what we've always been doing is having a shape, and we've been rotating it around an axis, right? And so we've also had ones where we may rotate it around the vertical axis or the horizontal axis. However, the shapes that we're getting every time we rotate something around a line is going to be either circles or is it going to be it's going to be washers. There's a new type called with cross sections where they just kind of they tell you what the cross sections are going to be like, and it's hard to picture these things, but I have a couple examples that have pictures of what's happening. So the volume of a solid whose base is a disk with radius r and whose cross sections are squares, you could think of like that. You could think of like this picture right here, where you could draw a square at each one of these, and this exposes my inadequacy to draw pictures in 3 dimensions, but you'd have an infinite number of squares that would go across here, and where it may be difficult to picture what the entire 3-dimensional shape would be, you could picture that this is an integral that goes from here to here, and each cross section is a square. So if you can find the formula for the area of one of those squares in an abstract way that takes into account the formula that's given, then you're going to be able to find the volume. I'm not going to do that one, but I'm going to show you another one. Here's an example where you're given region bounded by x equals 2 minus y squared and x is equal to y squared minus 2. And those are both parabolas. They're sideways facing parabolas. And the cross sections are isosceles triangles with bases perpendicular to the y-axis, and the angle between the base and the two sides is of equal length is pi over 4. Okay, so I'm not going to do this one. You can already tell that it's complicated, but what it's telling you is that this is the base formed by these parabolas or sideways parabolas, and you're going to get an isosceles triangle, and you're going to get infinitely many, and that's going to give you a 3-dimensional shape. I want to do one that I wrote, which I think is somewhat common for these ones. Find the volume of a solid formed by the base being y is equal to square root of 9 minus x squared in the x-axis, where the cross sections are rectangles with height, with height being half of the width. All right, so what does that mean? I'm going to show you what that means. So we know that our picture is going to go like this. It's going to be a half circle. And for each one of these places, we're going to get a rectangle. And the rectangle's height is half of what its width is. So maybe I want to draw it kind of like that. Okay, its height is half of what its width is. This one's a little bit bigger, so it's going to be a little bit longer. And you can picture you have these rectangles coming up out of this semicircle, and what's the volume going to be? Okay, well, the volume is going to be the sum of all those cross sections. Okay, what is the area of each cross section going to be? Well, each cross section is going to be height times width. Okay, so what's the height? The height is the square root of 9 minus x squared. Sorry, I want this to be the width and this to be the height. The width is square root of 9 minus x squared. The height is 1/2 of the square root of 9 minus x squared. And where does it go? Well, really it goes from -3 to 3. However, on a lot of these, I find it's easier to cheat by using the fact that you know that it's symmetric. So I can say it's going from 0 to 3, and I can multiply that by 2. And now when I do that, a lot of things work out to my advantage, which often happens when you pick the problem that you're going to go over. And I get the integral from 0 to 3 of 9 minus x squared dx, which is 9x minus x cubed over 3, evaluated from 0 to 3, which is 18 units cubed. So that's one example. There are other examples that'll have different shapes, and you just have to think through them. They're tricky, but you're living in a time when there's no limit to the number of resources at your fingertips through Google, and this is one of the sections where I encourage you to use Google to help you develop that mental representation of what those three-dimensional figures are, because I am clearly inadequate at doing that, as shown by my pictures. All right, good luck.